Welcome to Maths with EJD. We're still talking about real analysis, and in this video, the focus is on series of real numbers. In the last video, we had considered sequences of real numbers and some things, some rules attached to that. So now, series of real numbers. Interestingly, I have a previous playlist on sequences and series. Just go to my channel and you'll find all that there. So there, we focused more on, the whole idea of using actual actual numbers. It's not as abstract as what we have in this place. Okay. Let me see that now. Okay, we have this with playlists. Yeah, so sequences and series. Okay. Sequences, yeah. So interesting, we have 68 videos on sequencing and series. So starting with introduction to sequences, arithmetic sequences, geometric sequences, all the way down to applications and insight from special series. Well, okay, I think I also added to it generating functions because it's about sequences too and series. Then I added let's say, yeah, I added Fourier series, yes. Added Fourier series to it. Added binomial series. That's why it's that lengthy. But of course, these videos too are also uh so I mean the playlists are also separated. So I joined everything together, I still separated them in case all you're interested in is power series, for instance. You have power series. So imagine I have sequences and series here, but then I added power series. What else? Yeah, power series, for instance, binomial series, generating functions, Fourier series, all made up sequences and series right here. So if you want to see the quantitative side of sequences and series, you may want to go for that. But for under real analysis, it's more of abstraction. Once in a while, I may just try to I may try to express some things for you to see. All right. So, series of real numbers, an introduction. A series is simply summation n equals 1 to infinity of an with partial sums Sn equals summation from n equals 1 to n of an. So, I dealt with this in a quantitative way in the playlist I just showed you. So, and we say that the series is convergent if the partial sums Sn approach a particular S, which is real, and then it is absolutely convergent. So we have different types of convergence, right? So it's just convergence if Sn approaches S, which is a real number, and then it is absolutely convergent if the summation of the absolute An converges, and it is conditionally convergent if the summation of An converges, but the summation of An diverges. I might have taken some examples in those playlists if you want to check those out. Then we can talk about comparison and limit comparison tests. So we have direct comparison. If 0 is less than or equal to an, less than or equal to bn, that means an lies between 0 and bn, and the summation of bn actually converges. This implies that the summation of an also converges. That is a direct comparison test. But for the limit comparison test now, we have if the limit of an over bn as n approaches infinity is equal to c, which belongs to the interval 0 to infinity, right? Which is real in short. That so another way to express real is 0 to infinity. Is that it? No. Uh, okay. This is just a one side of the real number. The whole real number should be the open interval of minus infinity to infinity. That is real. So this is just positive real now. Okay. So that's R, like R positive. And in this case, the summation of an actually, if then summation of an converges, if and only if summation of bn converges in that case. That is the limit comparison test. That is the rule there. Then, I mean, I'm very sure I did this a lot under the sequence and series playlist. that if let L be the lim sup of the absolute value of an plus 1 all over an as n approaches infinity. So if by after you analyze this, you get your L to be less than 1, then that is absolute, that gives you absolute convergence. So in that case, you say the sequence an is absolutely convergent. If L is greater than 1, then you say it is divergent. If L is equal to 1, it is inconclusive, so you cannot conclude that the convergence of the sequence an. And that talks about the ratio test, right? I mean, I'm sure I did all that a lot under sequences and series. So I must have done ratio test, integral test, and all that. Okay, yeah, we also did root test. I remember I did root test there. So for root test, let L be equal to the lim sup of the absolute value of an raised by 1 over n. That is like the nth root of an in short. Nth root of the absolute value of an. So as n approaches infinity. In this case now, if L is less than 1, you have absolute convergence. If L is greater than 1, you have divergence also. If L is equal to 1, it is also inconclusive. All right, so it's about the same like the ratio test. Then we have the integral test too. So I did all this practically, like using numbers under the sequence and series playlist. So if you want to see more of that, please feel free. Then for the integral test now, if an is equal to a function of n with f positive and decreasing, so that's a monotone decreasing function, and it is continuous. So we say that it's the summation of an as n from n equals n to infinity actually converges if and only if the integral of f of x as from n to infinity actually also converges. So it's more like we are doing, so that's the integral test now. So we use integration to determine convergence. And then we have, so based on the integral test, now we have this kind of interesting bound that the integral from n plus 1 to n of f of x dx is less than or equal to summation of f of n as n goes to from n equals n to infinity, and that is less than or equal to n to infinity f of x dx. So in short, we are saying that the summation of f of n from n equals n to infinity lies somewhere between the integral of the function f of x dx from n plus 1 to infinity and n to infinity. That's what the integral test talks about. Then let's talk about the alternating series or the Leibniz test, right? So if an, okay, if an is equal to minus 1 raised by n minus 1 bn, with bn approaching 0 and it is monotone, then of course, if bn is approaching 0 and it's monotone, it means that bn is monotone decreasing, right? So we say that the summation an actually converges in this case. So this is for alternating series Leibniz test. And why is it alternating, by the way? When n, I mean, n cannot be 0 here. Let's say n is 1. When n is 1, you have minus 1 raised power 0, and that will be 1. So you have only bn in that case. Then when n is 2, you have minus 1 bn. When n is 3, you have 1 bn again. So you basically have minus bn and bn like that. So as bn approaches 0 and it's monotone, then the summation of an actually does converge. So the error bound is now absolute value of Sn minus Sn less than or equal to b sub n plus 1, like that. And then we can also have so I mean, apart from in the other case, I think I did more ratio test, root test, and integral test. So, but in the real analysis arena now, we have more tests. So in addition to those three, we have the alternating series Leibniz test, and we have the Dirichlet Abel tests. Okay, so here now we have that for Dirichlet, if partial sums an, which is summation from n equals 1 to n of an, are bounded and bn approaches 0, then the summation of a and bn actually does converge also. So the partial sums are bounded and then bn approaches 0, then the summation of an multiplied by bn actually does converge. So that's for the Dirichlet test. For Abel test, so if the summation of an converges and the sequence bn is monotone and bounded, then the summation of a and bn also converges. So talking about the Abel test. And then we have the Riemann rearrangement theorem. So if the summation an converges conditionally, all right, so for any s belonging to the real numbers, there exists a rearrangement with some S, and rearrangements may diverge to plus or minus infinity. All right. So the convergence is not guaranteed. An example is the alternating harmonic sequence, summation from n minus 1 to n minus 1 over n, which is equal to log 2, can be rearranged to converge to any target, right? So, and we have some proofs here for some of these things we've been talking about. So we have the first one, we talk about the P series via Cauchy condensation. P series under Cauchy condensation. Um, okay, I think I should have divided these things so that we can see the clear demarcations. So I'll do that as we go on, like this. So yeah, so now we have this. So P series via Cauchy condensation. So for condensation, you have summation of AN with decreasing AN is greater than 0 actually converges. So implies that summation of 2k raised per 2 raised per k A2k converges. So imagine take AN like that to be equal to 1 over n raised to power p. So in this case now you have 2 raised per k A sub 2k equal 2 raised per k, this 2 raised per k now all over 2 raised to power kp, like this, because here we have np. So if you have a2k, so that is 2 raised to power k with the p outside, and that is 2 raised to power. So if you simplify this whole thing now, this is 2 raised to power k all over 2 raised to power kp. So that's like 2 raised to power k minus kp. And if you factorize that, you have 2 raised to power k into 1 minus p. So in this case now, if p is greater than 1, you have, so that will give you a geometric series which converges. But if p is less than or equals to 1, it automatically diverges. So in that case, now we say summation of 1 over n raised to power p converges, uh, if and only if p is greater than 1. So that means summation of 1 over n raised to power p converges if p is greater than 1. And then if p is greater than 1, summation of 1 over n raised to power p converges. So you go both ways. So if you need to prove this, now you have to go back and forth like that. So that is P series via Cauchy condensation. And then we have the alternating series tests like we saw the other time. Uh, like I said, I want to do a kind of demarcation. So here, imagine you have the alternating series test. So which says that an is equal to minus 1 raised by n minus 1 bn as bn goes towards 0. In this case, now we say s2n is increasing while s2n plus 1 is decreasing. So s2n is the odd subsequence, like we saw. I think we saw that in the last video. So when we're talking about series of real numbers, so s2n is the even subsequence, while s2n plus 1 is the odd subsequence, right? So s2n is increasing. Of course, you know that here, if you have if you start with 1 now, so you're going to have 0. So minus 1 raised power 0 will be 1, but minus 1 raised power 1, so minus 1 raised power 0, 2, 4, 6, 8, and so on is 1. Whereas minus 1 raised power 1, 3, 5, 7, and so on will be minus 1. So you see now that S2n is increasing while S2n plus 1 is decreasing because it's going to minus 1. But so both are bounded. So S2n is bounded by 1, while S2n plus 1 is bounded by minus 1. So both bounded, and then we can say that S2n plus 1 minus S2n. So S2n plus 1 is bounded by minus 1 as we know it. So minus 1 minus and minus 1 minus 1, that's like minus 2. So, and then that goes to B2n plus 1. All right. And then we say that that approaches 0. So are we taking the absolute values then? So that approaches 0, and thus we say S2n plus 1 both approach S. So we can say that the summation of an actually does converge. And in this case now, in the other case, when we Bn is not part of it. In this case now we have Bn approaching 0, and that is what is making the whole thing converge. So we have borderline series with logs. So in this case, with logarithms, that is. So here now, so when you work with logarithm, things are a bit different. imagine that you have a summation of 1 all over n log n raised to power p, then the condensation implies that the summation of 1 over k raised to power p. So this converges just like what we saw just now, if and only if p is greater than 1, right? Then on this other hand now, you have summation of 1 over n log n log n raised to power p. So using integral test with u log x now, so this converges if and only if p is also greater than 1, just like the other one. So when we work with logarithms, and then we have some examples here, some examples like this, that summation of square root of log n over n will diverge. So that if you compare that to n log n raised per half, that's different. And then you have summation of 1 over n log n raised by 3 over 2. This converges if p is equal to 3 over 2, which is greater than 1. Of course, p is greater than 1 for this kind of thing. Then here you have sine n over n actually does converge following Dirichlet condition. And of course, yeah, so it does converge in that sense. And then you also have summation of n factorial over n raised by n, which converges absolutely if you go by the root test. So you want to check these things out based on the test you have outlined. Now, if you want to really understand this in numerical terms, you can check out the playlist on sequences and series where I talked about these convergence tests. And then we have the idea of conditional rearrangement. So to achieve target S now, I think that should be the supremum. You have to split series into positive pk and negatives minus qk. So, and then the algorithm will be to add positives until you have something greater than S, and add negatives until you have something less than S, and then you repeat. Then at the end of the day, you have oscillation approaching S, right? Oscillation in the sense that maybe it's minus plus plus until that oscillation is approaching S. Then alternating harmonic can be rearranged to converge to S equals 1 over 2 or any real S at all. And then we have some problems you may want to try your hands on. Okay, so we have these 8 problems. So you want to test summation of 1 over n log n raised to power p by condensation. Then you want to test 1 over n into log n into log n raised to power p. Then for summation of minus 1 raised by n minus 1 all over n, find n with error less than 10 raised by minus 3. Then show cos n over n converges following Dirichlet condition. Then test summation of 3n squared plus 1 over 5n squared plus 2. You can do limit comparison in this case. In this case, an idea like dividing through by the highest power of n, which is n cubed, can work right here. And then I can already suspect that you're going to get something like 0 in this case, which is a good answer, by the way. Then you can rearrange summation of minus 1 raised by n minus 1 over n to target 1. Then you can apply root test to summation of n over n plus 1 multiplied by n squared out there. You want to see if, okay, this whole thing divided raised by n squared. You want to see if that converges. Then you have bound tails of summation of 1 over n raised by p using integral test. You want to check all of this out. Let me know your solution in the comment section, either on Facebook or on YouTube. All right. So with this, I come to the end of this video on series of real numbers. So I think going forward, we'll be talking about things like limits, differentiation, Riemann integral, and everything. So watch out. This can be abstract, right? But you have to sit with it. And of course, if you really want to get quantitative stuff, like I said, check the playlist on sequences and series. That can give a bit more clarity on these things. So with this, I come to the end of this video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. All right. And then, of course, if you have not subscribed already, of course, you'll be missing a lot already. So why not just go ahead and subscribe? And of course, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Having done that, of course, we want to take it a step further, if possible, to become a member of the channel by clicking on join, and that comes with some special privileges, right? Ultimately, don't forget to comment, like, and share so that more and more people can have access to the great content I have going on here. Until I come your way again, keep doing maths right. Bye.